Well, welcome everybody. Our numbers grow. Uh, Welcome to our regular series of Vermont Sierra Club community conversations. We're really excited to have a great show tonight with Dr. Lesley-Ann Dupigny-Giroux of the University of Vermont, who is our state climatologist, and Dr. Janel Hanrahan, who of Northern Vermont University. And we're excited to have a discussion tonight about Vermont's climate. Where are we headed? How does this make a difference to policymakers? How do you take the temperature of the planet? What do you do about it? So it should be a very exciting discussion. And I will say to everybody who's here, we will have a lot of opportunity for discussion and questions. Please feel free to put your questions into the chat box, and we will get to as many as we can after a brief presentation from both of our guests. We are recording this tonight, and it's being streamed live on Facebook. So if you really prefer not to be seen, you can close your video. But we love to see faces, and so if you want to join us that way, it's great as well. We do request that you keep yourself on mute for the most part, which seems to work very effectively by my equipment here, and unless you have a question, and that really helps keep down the background noise. So thanks everybody for that. And with that, I will pass it along to Dr. Dupigny-Giroux. Welcome.
Well, good evening, Steve, and thank you for that very gracious welcome. Good evening, everyone. It's a pleasure to be here and to be sharing this space again with Dr. Janel Hanrahan of Northern Vermont University at Linden. Janelle and I have been doing these sort of tag teams for the last, 4 or 5 weeks now, and so this is the third one that we're doing, and we're having such a blast doing it that we thought we'd do it one more time with a little bit of a twist. So this evening, what we're going to do is, instead of doing Climate Change 101 in the traditional sense, we're going to be using a couple of lenses to look at and to talk about climate change. And so the two lenses that we're going to be using are vulnerability, particularly human vulnerability. And we're also going to spend a little bit of time talking about uncertainty in the information, uncertainty in our understanding of some of the processes, and how do scientists work through uncertainty to arrive at a more clear understanding of what's taking place in the weather and climate around us, both from a regional perspective of a local perspective. So again, Lesley-Ann Dupigny-Giroux, faculty member in the Geography Department at the University of Vermont, a Vermont state climatologist, and also the president of the American Association of State Climatologists. So I've kind of broken down my piece into 3 big buckets. The first one is looking at some of the elements of climate change that I want us to kind of keep in mind as we step through. Then we'll talk about human vulnerability, and then we'll end with some environmental vulnerability. So hopefully a little bit of a change from some of the things that you may have seen before in the past. So when we think about some of the dimensions of climate change that we're looking at, I always like to lead with, because it's critically important to look at what makes up our climate and what makes up the changes that we see in our climate. So you've got 2 diagrams, both showing you essentially the same thing, with the ways in which we can look at climate change in terms of changes in not just emissions of greenhouse gases, but changes in our ecosystems, changes in the things in the atmosphere, so the atmospheric chemistry, pollution, and so on, the aerosols that we breathe, the aerosols that are emitted into the atmosphere, and how all of those are interrelated. That's what all of these arrows are showing you. And so when you think about how our climate is changing, it's all of these various elements that are shifting or the concentrations of them are actually shifting as well. So that's one way of thinking about it. And then when we think about the actual processes, the systems, the variables that are changing, it's not just temperatures, it's not just precipitation, but it's also where our winds are, where storm tracks are, types of clouds, how humid the air is, soil moisture, sea level rise. All of those are elements of how we understand how our climate is changing in here. So trying to shift the notion from only temperature, from only precipitation to some of these other elements that make up our climate as a system. So, in thinking about climate as a system, a lot of times, if we were doing this in person, I'd ask you to sort of like raise your hand for which one of these or which parts of this diagram, which is one of my favorites, resonates the most with you. And is it the ways in which we change our climate? So, is it things like our greenhouse gas emissions? Is it changes in land use patterns? Is it agricultural processes? Or do you resonate more with the impacts of climate change? So, ocean acidification, or lilacs blooming a little bit earlier, changes in your bird populations, change in habitats. Do those resonate more with you? Or do you resonate with the types of strategies that we are trying to implement in terms of either mitigating against climate change or adapting to our changing climate? And so it's good to get a sense of where this makes the most sense to you. And so another diagram that I always like to use is this one that shows us the ways in which when we look at these actual numbers of either temperature, precipitation, soil moisture, sea level rise, and so on, thinking about how do we quantify that change that we can talk about as climate change, right? And so whether it's a jump in the record like we would tend to see in the geologic record, whether it's trends, which is either increases or decreases over time, and that's what we usually think about when we think about changes in our temperatures. And then the one that is becoming particularly important for us is this notion of changes in the amount of variability that we're seeing in the system. And we saw that again this year with looking at particularly cold temperatures over the last few weeks, and then now we're getting back into the warmth. And so how does this sort of play out for us? Because it's important in looking at how vulnerable we are. And so this is a slide that sort of grounds the entire piece that I'm going to be talking about in looking at vulnerability across the spectrum. And so those flips between high temperatures and low temperatures, excessive moisture and deficits in moisture. One way of looking at that is this notion that we have that ability to go between different states, from moisture to droughts, for example, all in the same year. And so 2011 is a great example of that, where we were in a drought for a lot of the year, but at the same time, we had those spring floods, and then we had Tropical Storm Irene. And so this notion of going beyond those limits, those thresholds that we have as humans, as a society, is critically important for us for looking at this notion of vulnerability. So I teach natural hazards at UVM. And one of the things that we talk about in my climatology and natural hazards class is this understanding of exposure to different types of events, the risk that that poses to us from a societal perspective, and then our vulnerable populations. And so this is the lens, this is the frame that we're using and thinking about this evening. And it's also the frame that was used in the fourth National Climate Assessment, or NCA4, which was released in 2018. And so NCA4, National Climate Assessment, the fourth element of it, used what was called a risk-based framing to talk about climate change, to explore climate change. And so when we were writing this, I was fortunate enough to be the lead author for the Northeast chapter. When we were writing this, these are the questions that they asked us to think and keep in mind. What is it that we as Northeastern residents value, and what is at risk in the Northeast? And what are some of the outcomes that we want to avoid based on these things that we value a lot? And then what would happen if we didn't have mitigation, if we didn't have adaptation taking place? And then the last piece is what's the sort of trigger point, that threshold beyond which it's a tipping point and things move to a different state. And so these were some of the questions that are part of this risk-based framing that we use for the Northeast chapter of the fourth National Climate Assessment. So in thinking of vulnerability and thinking of the spatiality, the temporality of vulnerability, one of my colleagues at UVM, Dr. Sherry Morse, this is some of her work in looking at how do we think about who is vulnerable? How do we think about elements of vulnerability? And it goes beyond race or ethnicity. It goes beyond health status. It goes beyond socioeconomic status. It goes beyond immigration status. It goes beyond language and gender, place-based pieces. In all of these sort of come together in helping us to understand vulnerability from an individual level, but also from a community level. And so in the fourth National Climate Assessment, there was a piece in the adaptation mitigation chapters that specifically pull that out from a human perspective. And it talks about populations, including older adults, children, low-income communities, and some communities of color are often disproportionately affected by and less resilient to the health impacts of climate change. And so specifically speaking to human populations and the vulnerabilities that we have here. And we saw that last year. So we went into the pandemic, we went into a lockdown in March, and we started to see the ways in which the COVID pandemic was actually sort of like an additional stressor, a stress multiplier, if you will, for this notion of vulnerability on top of climate change that was continuing to progress. And so a lot of the heat waves that we saw last summer were exacerbating a lot of the underlying vulnerabilities in populations. And so heat stress is one of those elements of our changing climate that we're particularly interested in. And then the additional stress of having the pandemic on top of that. So when we think about heat stress and we think about us here in Vermont in Northeast, some of the work that Dr. Evan Oswald, who was a postdoc with me a few years ago, did some work with our colleagues at Department of Health and found that we don't get a lot of days that are over 90 degrees as a trigger, but what the threshold should be for us is a slightly lower one, so it's 87 degrees. And so now when the value gets to that point, the Department of Health works with the National Weather Service to send out a warning to all Vermonters, and with a special emphasis on our vulnerable populations, that there's a heat warning going out. And another element of human health is, of course, increased incidence of Lyme disease, increased incidence of ozone at the ground levels where we walk around, because that has implications for smog development, particularly in our valley areas. And so that 87-degree threshold, this is how it sort of plays out across the state, where you tend to see more values in the Champlain Valley, more values in the southeast part of the state here, fewer in the kingdom where Janel is, because of the higher elevation, lower temperatures that are part of the kingdom. That's one of the characteristics from a climate perspective. The other piece in terms of human health is people moving from one place to another in terms of either health issues or migration, or in the case of leaving certain populated areas and coming to lesser populated areas like Vermont, in looking at refugia from COVID-19, for example. So this was a CNN snippet that I pulled out back in April last year, and we started to talk about, will we be seeing COVID-19 refugees? And we have been seeing folks coming into the state as a result of relocation due to the pandemic itself. Now, one of the pieces that the pandemic actualized was not just migration, not just heat waves, but then we had a couple other pieces that all came together last year as well. Particularly remarkable year from a hurricane perspective. There were at least 5 landfalling hurricanes in the southern part of the US. And so all of this sort of comes together for us. Fire was another big piece for the western states, and again, all of this is taking place against the backdrop of the pandemic. And so when we think about the Northeast as a region, this is one of the diagrams that we created for the National Climate Assessment. When we think about the Northeast as a region, we think about some of the things that are unique to us that are particularly at risk to climate change. We've got a rural-urban dynamic going on. We've got inland and coastal. We have our cultural heritage, which is one of the prize points of our region in here. We have the topography that sets up different types of vulnerabilities from an environmental perspective. And then we have the length of the settlement that has occurred in the Northeast as well. And so in one of the chapters in the Northeast assessment, we were able to try and quantify the impact of the changes in, for example, air quality. So having more days of higher ozone concentrations and the potential for smog, and we'll see some of those higher values are projected for the Northeast, and what that means in terms of individuals who work outside, particularly, and the ways in which that could affect the number of hours that could be worked outside. And so we've got this ability to sort of look at this and try and tease out what it means for various types of outdoor activity. And what you're looking at on the left-hand side is these upper and lower limits of the what are called representative concentration pathways, which Janel might be getting into as part of her talk a little bit later, in the sort of business as usual, which is this higher level, the representative concentration pathway 8.5, and then the more aggressive way of trying to mitigate against both your greenhouse gas emissions, but also some of the other land use types of activities and choices and policies that we bring about as human beings. So this is by way of prepping in and leading into some of the things that Janel might be talking about. Janel, shake your head if you are going to be talking about that. Okay, good. All right. So Janel will talk a little bit about this, and this is to sort of do that connection between the two of us in looking at how do we look at some of these elements of policy from a climate change perspective. So the last piece of what I'm going to talk a little bit about is the vulnerability that we have from an environmental perspective. And so when we think about what that looks like, we can look at it from either a precipitation, moisture perspective, or from a temperature perspective. And so as we see fewer and fewer cold nights and more warm days, we see that shift in the entire what we call distribution, so that you see more hot weather in terms of the actual values, but also the number of days, and fewer of those really, really frigid nights when the temperatures drop. So that's one way that we can look at it from an environmental perspective. And then in terms of actual precipitation, fewer of those really, really light drizzly types of days, and more of the days when you have large amounts of rainfall falling in extreme events. And why that is important is because it then plays out in the different types of disasters that we can see. And the one that you see in green, which sort of dominates most of these bars, are what are called severe storms. So your severe storms are your thunderstorms that occur, and you're probably a little bit surprised that those are such a large component of what causes a lot of disasters, because I know you're probably thinking, well, isn't it usually hurricanes and tropical systems that do a lot of damage? Yes, they do, but it's the sort of everyday other types of severe storms that actually produce a lot of damage as well. And so this is a graph from the National Center for Environmental Information, NCEI, that starts in 1980 and goes to the present, so 2020. And it shows you the billion-dollar disaster. So every time there was a billion-dollar disaster, they mapped it on here, and you're seeing that increase in these billion-dollar disasters over time. And like I said, most of them are due to these severe storms, okay? So the billion-dollar disaster, if you want to kind of Google that and maybe look back at how this has changed over time. So part of those billion-dollar disasters are, of course, tropical cyclone whether they're hurricanes or cyclones or storms. And Northeast is not exempt from having a lot of these move over us. And so this is just to give us a feel for the various tracks that some of these have taken over the past. So the Long Island Express in 1938 pretty much came up the Hudson Valley into Champlain Valley and moving on north. Hurricane Floyd in 1999, which this is a storm here by, all right. And that one produced like 14 inches of rain on Mount Mansfield. And then Irene, which produced about 8 inches or so in the southern part of the state in here. So we're not immune to having these storm systems move across us, and they bring a certain amount of precipitation depending on where that storm track actually falls. So thinking about these systems, thinking about the fact that both the amount of precipitation, the amount of warming, the changes on the land surface itself, all of these produce a lot of these extreme events that we've been seeing so many of in the last little while, and the sort of range of impacts that we see, not just on a local scale, so like on a city scale, but also on a more regional scale as well. So thinking about the sectors in the state that are particularly susceptible to climate change, we can think of things like agriculture, forestry, human health, emergency management, tourism and recreation, and of course, infrastructure. And in terms of infrastructure, it's our roads, our highways, it's our railways, airports, the electrical grid, water supply, and our critical infrastructure. And when we look at it, there's certain parts of our cultural heritage that make our infrastructure, particularly the road infrastructure, very vulnerable to our changing climate. And a lot of it is because our valleys are very narrow, very V-shaped. And so if you look at a map of the state, you tend to see this pattern repeated over and over, where you've got your water course in here, that's the blue, and your roads are literally a couple feet away because there's nowhere else to put it in the valley. And that sets up the ability to notice that there are always repeat locations of flooding because of that relationship. And so Waterbury, the town of Waterbury here, is an example of when this happened in Irene. And we had those pinch points here where the Winooski and I-89 sort of like came very close together here and sort of trapped the residents of Waterbury within the boundaries in here. And so Irene, if you think about it, this is a map that was produced by Jonathan Croft of VTrans. And what it is a 1927 flood map. That's the parchment area here with all of these black lines. And the places that were affected in Irene, those are those colored lines that you're seeing here. So the yellows and the greens and the reds. And I know you can't see this very well. So if I blow up a little bit to the central part of the state, you can see right off the bat that the roads that were affected in Irene, those are those colors again, and the roads that were affected in 1927 are pretty much like this, right? Because the roads haven't moved in over 100 years. And so putting together this sort of geospatial information allows you to see where the infrastructure vulnerability is. You can actually try to use that to make a difference in terms of planning for changing amounts of precipitation in a changing climate. So to wrap all of this up, for me, there's a lot of this dynamic as a geographer between what we do as human beings and the environment, who are vulnerable, whether it is from an information perspective, whether it's from a location perspective, whether it's from a physical geography perspective. And when I think about this, I always try to do it from a system science perspective so that I do get all of those various moving pieces in here and look at it from all of the scales, from the local scale all the way up to a more regional or higher level planetary scale. And a lot of this information, a lot of this understanding changes relatively quickly, which is great because it keeps you on your toes as a scientist. And so you need to be flexible, nimble, and quick. And what keeps me going in terms of always being on the lookout to help share some of this knowledge is that I truly believe in the resilience of us as human beings. So with that, I am going to stop sharing my screen and I am going to turn it over to my dear colleague and friend, Dr. Janel Hanrahan.
Thank you, Dr. Dupigny-Giroux, except you had mentioned that we're going to do this one more time, and I hope it's not our last time. All right, So let me go ahead and get myself sharing here. And I'm going to do what I do with my classes is get you all situated on one screen. So if you have video showing, then I can see you. And then I put my PowerPoint on the other side or whatever screen that I'm sharing with my students on the other one. So I like to start with this image oftentimes when I'm presenting on the topic of climate change, because I think it just does a really nice job of showing our atmosphere from a perspective that clearly we don't normally see. So if you can just kind of see this blue haze here cutting across the sun and showing how our atmosphere just kind of fades off into space. And oftentimes we think that our atmosphere is really big, right? You look up and see an airplane flying over, or you see the height of the clouds, and you think that the atmosphere is just massive, and how could we possibly modify it? But actually, our atmosphere, the vast majority of it is within only about 10 miles of the surface of the Earth. It's really, really thin. And this thin blue atmosphere is the difference on our planet between having life on our planet and not having life on our planet. In addition to the existence of the atmosphere, which is important for getting our global temperatures above freezing, which makes it habitable, it also depends on what makes up that atmosphere, right? So fortunately for us who live on planet Earth, there are greenhouse gases in the atmosphere. We do in fact need to have them in the atmosphere. Number one, to keep temperatures above freezing, but also so that we don't have these crazy temperature swings when we're facing the sun and away from the sun. And so this atmosphere is incredibly important for sustaining life on Earth, and more specifically, the exact life that we have right now and in the places that we have it on Earth. And as we continue to add things like carbon dioxide and methane, all of that to this atmosphere, then of course we start to see some pretty drastic changes. And I'm sure many of you have seen graphs, maybe something that looks like this, but taking a look at the ice core records going back almost 1 million years. And just for reference, modern humans evolved about 200,000 years ago. So it's quite a bit longer than that. But oftentimes we take a look at the amount of carbon that's in our atmosphere. So we're well in excess of 400 parts per million today. We know that that's on par with about 3 million years ago, but oftentimes we don't consider the idea of how quickly we're adding this carbon to our atmosphere. That in itself is also unprecedented. And this just doesn't go back just 3 million years, but really for the life of our planet, we don't know another time where we have added this much carbon to our atmosphere this quickly. And so this helps to put this into perspective. We're over here, we're in the past 800,000 years, coming through the present, going through all sorts of glacial, interglacial periods. And then this right here, which ended about 10,000 years ago, is our last transition going from a glacial period to an interglacial period, the current Holocene, which has been in place now for about 10,000 years. And even at this point, when the Great Lakes were being carved out, when the North American ice sheet that had as much mass as Antarctica today was retreating, even at that point, we were only looking at about 10, maybe 20 parts per million every 1,000 years that was being added to the atmosphere. And you compare that to just the last 100 years, we've added in excess of 100 parts per million. So this rate of change in itself puts us in a situation as scientists where we think we have a pretty good idea of what things are going to continue to look like, but we don't have precedents. We don't have a past climate that we can really look at to say that, yeah, we think our models are correct for this reason, because this sort of thing has simply not happened in Earth's history. And I like the analogy of just thinking about a big loaf of bread in the oven for those of you who like to bake, or maybe some of you even have a loaf of bread in the oven right now. I'd like to come to your house if you do. But instead, we can think about Earth as being like a really big loaf of bread. And what we're doing essentially is we're turning the temperature dial on the oven. So I like to think about that with the carbon that's increasing in our atmosphere. It's kind of like turning that temperature dial and then putting the loaf of bread in, and then continuing to turn the temperature dial and continuing and never letting the bread get up to temperature. That's essentially what we've been doing. So Earth's global temperature will continue to increase even if we stop turning the dial, which is analogous to we no longer put carbon in our atmosphere. But even after we stop turning it, Earth will continue to increase in temperature and energy, even long after that happens, for decades, most likely. But we do in fact know that global temperatures are increasing, and Lesley-Ann pointed to a lot of the changes that we've seen in the historical data. But just taking a look at our global temperatures, the black line here is observation going back to the late 1800s. We know that we've had a pretty substantial uptick in global temperatures. Science now shows that since about 1960, the vast majority, if not 100% of this warming is in fact directly attributed to increases in greenhouse gases. And then the gray line that's on here is a model simulation, which was selected actually from the most recent CMIP-6. This is a huge number of model simulations that are completed all around the world that help to inform the IPCC reports. So this is one of the models that'll help to inform the next IPCC report, which is going to start to come out at the end of this year. And what we can see is that the model doesn't match observation perfectly. So for example, there's like the Dust Bowl period right here where global temperatures were high and the model dropped down. But when you're looking at a climate model, it's not like a forecasting model where we want them to align in time and space, but instead we want to make sure that the statistics are well represented. That's the sort of thing we look for. And what we can see is that this positive trend that we've had since about 1960 is fairly well represented by the model. And so once we do this, what we call a hindcast simulation with a model, then we can start to play it forward to say, okay, what do we think might happen moving forward? So I have a little video here. I'm not sure how well this will come across on your screens, but the important part is the very last image. So if we take a look at this current trajectory, so Lesley-Ann had asked me if I was going to talk about RCPs. And I lied a little bit because this is not actually an RCP. It's actually one of the newer socioeconomic pathways that's going to be coming out with the IPCC report. But we still oftentimes think about this as either business as usual, or I like to say worst case scenario, right? Because business as usual seems like, we're locked in and this is going to happen. But instead, this is really thought about as worst case scenario. But it's important to point out that the warming that we've seen and all of the impacts that it's had on our Earth system to date pales in comparison to what we're in store for if we don't rein this in and get things under control. So taking a look at that trajectory versus another possible and very possible trajectory, which is this alternate trajectory, which is extreme mitigation. So we decide that we're going to be more efficient with our use of energy. We're going to change where we're getting our energy from. And ultimately, we're going to figure out a way to start getting carbon back out of the atmosphere. As I said, we're still locked into some warming for a few decades, but ultimately we could end up with a climate system that's actually really similar to the one that we're enjoying today. Still warmer than pre-industrial times, but similar to what we're experiencing today. And so it's important to note that the difference between these two vastly different climate systems is what humans will do, how much carbon we put into the atmosphere. So has climate changed? Yes, but we can't throw up our arms and say it's all done because this is all that's happened so far, right? So there's a lot more warming in the pipeline and there's a lot more that can still happen. Let me just skip forward here. And I just have one more slide to show, and then I want to just come back to all of you for some discussion. So this is a figure that one of my students put together. I was for her capstone project this past semester, where we were taking a look at model simulations. There's a lot going on in here, so I'll just try to break it down for you. But we were taking a look at model simulations under RCP 8.5. So I guess I did throw that in there a little bit, but it was RCP 8.5, and trying to understand what things are going to look like here in Vermont, specifically in this case with this idea of having tropical nights. And so in this case, when we're talking about tropical nights, what that means is like comfortable sleeping temperatures. So if it's a tropical night, it's uncomfortable. If it's not, then it's supposed to be comfortable sleeping temperatures, assuming you don't have AC. And so she looked at two different global benchmarks. So the first one here is 1.5 degrees Celsius, which might sound familiar because that's a common benchmark that's discussed with the Paris Climate Accord. And so when global climate temperatures, when global temperatures are essentially sustained at 1.5 degrees Celsius, then we have this histogram that's over here on the left-hand side. And don't worry about the frequency values or anything here. All we need to focus on is the fact that we're talking about 2 weeks of uncomfortable sleeping, about 2 weeks of uncomfortable sleeping on average. And by the way, you can compare this to recent history, which was the late 1900s. We were looking at less than a week. So she had computed the historical mean of being 5.5 days. So we've already gone from about 5.5, or we will soon go to about 13.5 if this holds true. But if you remember, we had two very different possible futures, right? And so this one, if we kind of get locked into that one, would be that extreme mitigation scenario. In fact, some would say extremely unlikely. But then we also have this 4 degrees Celsius of warming, which most models have us hitting by the time we get to about the year 2100. So kids today will essentially be in retirement by that point. And we can see that this is a very different climate system with respect to comfortable sleeping nights. So we jump from this 2 weeks of uncomfortable sleeping to well in excess of a month of uncomfortable sleeping here in Vermont. And another key point here, again, kind of getting to this idea of predictability or just uncertainty, speaks to, I was one of the bottom time series that Lesley-Ann had shown on one of her earlier slides where she was talking about variability. So this is just another way to express that. So we can see that if in fact we got to this 4 degrees of warming, that not only has the peak kind of shifted to the right, but it's also spread out more. And so what that means is that, yeah, on average, we'll be at just in excess of a month of nights that are uncomfortable to sleep, but it's also not terribly unlikely under this scenario to reach 2 full months of evenings that are uncomfortable, right? But we could also have some years where we have more comfortable sleeping nights. And so it's not only when we're talking about uncertainty with future projections, we're not just talking about, are we going to end up with the blue or are we going to end up with the orange, but also once we get to the orange, what's going to happen in terms of just the day-to-day, year-to-year, and decade-to-decade variability. That in itself lends some uncertainty. So as promised, that was going to be my last slide. So I'll go ahead and stop sharing. And Steve, I think I'm going to hand it back to you.
Okay, great. Wow, thank you for, it's a lot of information to download quickly. And it really sketches out a challenge there. So everybody, as you think about what you've seen, if you have questions, please enter them in the chat bar. We'll keep track and hand them off to both of our speakers. So I have a question that that relates to the sort of both the last things you were just talking about, Dr. Hanrahan, and also Dr. Dupigny-Giroux. You had your slide showing the days over 87 degrees in Vermont, which was interesting to me. First, interesting to realize that we might have a different threshold for what we call hot here than somebody who's used to it, say living in Alabama. You know, so days over 87 were those numbers sort of current averages that you had on your slide? And what happens if we get to this, say the RCP 4 or 8 scenario? What happens to those numbers? Do you have a sense of that?
Just before I answer that, I just wanted to say, Janelle, that was an amazing piece of work. You could please tell Samantha that for me, and I would love to see the rest of her project or her thesis. Really, really nice piece of work. And then to get back to Steve's question, that 87 was done in 2015. And I've actually started conversations with some of my colleagues at Department of Health to revisit some of that work to see if those values need to be changed. So definitely keep your eyes peeled to see if we do need to shift them back up a little bit. But historically, we don't get those 90 degrees, like you were saying, in the southern parts of the country or in the western parts of the country. And so it makes a difference in terms of human comfort, like what Janelle was just talking about, and whether you can sleep at night is one piece of the puzzle, but also how hot do you get in the daytime, because then comes the air conditioning piece, and how do you sort of keep your houses cool if the temperatures get up above a certain value for an extended period of time. So it's one of those, again, that's human environment interaction piece that's critically important. And if we need to tweak that threshold, it's one of the things I'm going to be definitely looking at.
Great. We have a question here. Let's see, Nell has asked about humidity and how that factors in. And I guess, you know, you might have multiple factors. coming in at once. That must make it tough to assess and predict. But question about
Nell, did you want to put your mic on and say a little bit more about what you mean by humidity?
There we go.
Great.
All right. Yeah, we were thinking of humidity and temperature. You were talking about comfort and sleeping. And certainly, one of the concerns we've heard in many parts of the world is the combination of humidity and temperature. And not just from a sleeping standpoint, from just survivability in many cases, critical temperatures. And we certainly both of us are from the Northeast originally. So the idea of humidity in the summer sounds pretty consistent. Has that been factored into any of the studies that you've been doing?
So I grew up in Trinidad, which is in the West Indies. So I have a different relationship with humidity. And for me, it's always like, it's not humid enough, which I know I can't usually say out loud because, again, my body's used to a different amount of humidity. But I do definitely appreciate that relationship between high temperatures and high humidities, because it's a human comfort factor, both from a daytime perspective, but also from a nighttime perspective. And it's also important from a precipitation generation perspective. So we talk about what are called your dew point temperatures. And if your dew points are high, then it's really, really uncomfortable. But high dew points are kind of great because they also allow you to have a lot of condensation and precipitation falling. So there's a little bit of a trade-off here. And I know, Janelle, when you're doing forecasting and teaching the students about forecasting, what are some of the things that you bring in terms of a dew point and humidity aspect?
I don't dare say that I teach short-term forecasting because I actually don't. And so, in fact, that's become a joke in my classes. When I say I created a forecast based on this dynamical process, students laugh. So I can't actually speak to that. But one thing I will just briefly mention is that when we're talking about humidity, oftentimes we're referring to what we call relative humidity, which is kind of like how much the atmosphere can hold compared to how much it is actually holding. And that's complicated because what we're doing is we're increasing the capacity for water vapor in the air. And then we're also putting more water vapor in the air. And so it's like a fine balance between the two. And so I believe that some areas may in fact decrease in kind of this relative humidity idea. And that's really how sticky it feels versus how much moisture is actually in the air. But we do also know that the actual amount of water vapor that's in the air today is about 7% higher than what it was in the past. And so we fully expect that amount of water vapor to increase in our atmosphere because 70% of the surface of the earth is ocean. And so if we have a higher capacity for water vapor in the atmosphere, it will in fact take it up. So that's something that's marching right in line with what we would fully expect.
And then related to that is when it actually precipitates out and you have these heavier rainfall events and these extreme events with lots of rainfall falling in a short burst of time because there's so much moisture in the atmosphere, right? So it's all part of that system again. Thank you for that question. It was an awesome one, yeah.
Great, thank you.
We have a question from Zara Reeves about mature forests, and I guess this is more of a mitigation question. Sarah, do you want to ask your question?
I just found the unmute button. Yes, I attended on Zoom some lectures by Dr. Bill Muma, who was describing the impressive amount of carbon sequestered by mature forests, and especially in the Northeast, that this is, in my perspective, almost an obligation for us to do our part for our hemisphere because of the mature forests we have, which are now being threatened with the typical so-called sustainable cut without recognizing the difference in the amount of carbon sequestered if you have really almost 100-year-old trees compared to those that are 50 years old. So,
And go ahead.
yeah, so can't we really get behind that and push that as something that we in Vermont can do to mitigate climate change?
Mm-hmm. And that point that you brought up is one that members of the Vermont Climate Council are actively thinking about in terms of what are called nature-based solutions. How do we use our standing forests or standing biomass to actually sequester a lot of that carbon? And also related to that, how do we make sure that our soils are healthy so that they can also sequester carbon? So it's something that you're definitely in line with a lot of the thinking that's currently going on around the state. Like I said, Nature Conservancy is helping to lead some of that charge and some of the work that they're doing in conserving forest lands, but also needing to work with private landowners to make sure that this is an entire statewide initiative. But that's a definitely important point that you brought up. Thank you for bringing it up.
Dr. Hanrahan, did you want to add to that at all?
I guess the only thing I would add is that, well, deforestation is incredibly important. In fact, we know we're adding carbon to our atmosphere every single year due to deforestation in addition to fossil fuel emissions. I also think it's important to keep into perspective that we can't plant our way out of this. We can't just keep emitting carbon and then plant trees to kind of make up for it. And just to illustrate that point, if we take a look at what's called the Keeling curve, so it's the longest continuous record of atmospheric carbon dioxide that started in 1958, we can see that there's annual fluctuations in atmospheric carbon dioxide, and it goes up and down by about 4 or 5 parts per million. And that is a direct result of, in the summertime, our trees grow, it takes carbon out of the atmosphere through photosynthesis and then releases it again in the fall and in the winter. And the northern hemisphere dominates because there's a lot of land there, but we have this annual fluctuation that occurs. And if you think about, a huge part of the northern hemisphere where the trees are losing their leaves and regrowing it, and that in itself only contributes to like 4 to 5 parts per million of change compared to in excess of 100 parts per million that we've already put into the atmosphere. Just kind of keeping that in mind, that we need to keep our trees and we need to plant trees, but that needs to be part of the solution. It can't be the only solution.
Excellent point. I think when the, a couple of years ago, the IPCC came out with a report looking at what it would take to stick to 1.5 degrees of warming. And they said we have to do all of this mitigation that we possibly can and bring our emissions down to 0. And then beyond that, we also need to be increasing the amount of sequestration that we do, whether it's hopefully primarily through nature-based, the forests, the soils, oceans, kelp forests in the oceans, wetlands, terrestrial wetlands too, all that, beyond all the mitigation that we possibly can. So pretty essential. Yeah, great question. We have a question from David Bray. David, welcome. Do you want to turn your unmute and possibly turn your video on?
Yeah, sorry. The question is, as the seas rise in South Florida and the Southwest US enters into a megadrought, are there projections on affluent climate migrants or refugees fleeing to desirable, cooler northern locations like Vermont?
And that's an area of research. A couple of my colleagues at UVM are actively looking into that. If you would love to know more about that, if you send me your name, I'd be happy to connect you so that they can share some of that active research that they're engaging in right now.
Okay, thanks.
No problem.
It is a topic that comes up regularly in discussions in your Science and Data Committee and the Climate Council. I know that.
Absolutely.
Yes. And I think that to add to that, there certainly are areas where they're already talking about relocating entire communities, and if you go far enough ahead, and it's kind of the inevitable several feet of 2 to whatever number of feet of sea level rise, there are quite a few people,
Mm-hmm.
and that's going to have impacts. I don't know if those folks from Florida are going to come to Vermont. We'll see.
If I may, I don't have data on the projections, but I do want to point out a really important word there that David had inserted into his question, which was affluent. Just thinking about it's the people who can move, the people who have the ability to move and adapt to climate change in that way. And it's, those who are maybe a little less well off are going to have a harder time making those changes.
Mm-hmm. Absolutely. Absolutely. As Jim Antal points out, it's referred to as planned retreat. Are there any other questions out there?
I think Jim just typed in, he said he now has a question.
Jim, yes, please.
Hi, I was a little late to this gathering, but even being a little late, I appreciate what I've heard so far. So I just wanted to share with our guests and also with the group a thought I had last month. I think many of the folks here know that NOAA released its new normal temperatures in May of 2021. And it seems to me that that would be an opportunity for meteorologists all over the country to recognize that by shifting the sort of decadal averaging system, which NOAA does every 10 years, what we do is we're like the frog, in the warming pot of water, using our ability to acclimatize to almost anything. And, we just have a new normal here. It's just a half a degree more than the old normal. And, gradually, obviously, temperatures are going to rise. Why don't meteorologists use this as an opportunity to introduce a new reference? And we could rename so-called normal temperatures as what we're used to, and then have a different measure called departure from normal, and use the same standards that climatologists use that go back before the industrial age to measure normal. I wonder what our two guests might think of that idea.
So thanks for that question, Jim. And what you're referring to are what I call climate normals with an S. And it's actually mandated by the World Meteorological Organization, WMO. There are 4 different ways of doing climatological normals, and the one that you're referring to is the one that's most commonly known or most commonly used, but there are 3 others that are also used. And the way in which they're done is you need to have at least 30 years for the statistics to be stable enough to create one of these 30-year averages. And they're very set rules that the WMO puts out in terms of how these normals are created. And so they always start with a year that ends in a 1, and they end in a year that ends in a 0. So they started like back in 1961 to 1990. And then every time you get an additional decade of information, it slides forward, because what you're trying to do is to capture the most recent representation of your climate, so that as you make plans for, let's say, sizing culverts, as you make plans for growing degree days, all of those are part of the normals that are computed on a 30-year time frame. And so the National Center for Environmental Information, NCEI, which is in charge of actually producing and computing these normals that, as you said, came out on the 4th of May of this year, what they also did is they worked with one of the regional climate centers to actually have all of the years of record, so that anybody who's interested in looking to see what the averages look like going back into the past all the way up to the present, you can actually see how those changes in the 30-year time frames look over time, so that you can gather the effect of a long period of record versus a short period of record. And you can see the very marked changes in your temperatures, precipitation, humidity values, and so on as you kind of step through time. And so when climatologists say normals, that's what they're talking about, which I've always found kind of interesting in the use of the regular term normal, which is sort of like expected conditions. And so definitely take your point in terms of the lexicon, in terms of the use of the word. And it's one of those pieces that I always work with when I teach climatology to help my students understand the generation and the use of these 30-year averages, and then why we would want to look at like a century-long average, for example, and how that changes the understanding of some of the variables that we're looking at. Janelle?
I don't have a whole lot to add to that, but I do think that the idea of having broadcast meteorologists talking about these types of events on TV and bringing the science into the American household and the global household is just incredibly important. And there are some really amazing organizations out there who are currently working with their broadcast meteorologists and helping them to sculpt that story, because broadcast meteorologists are typically not trained in climatology. And so we're working with them now to try to improve that messaging.
I think the Weather Channel went through an evolution like that over the last, say, 10 or 20 years. I see Jack Cushman has his hand up. We'll go to Jack. And
thank you, and thanks both of you for your work and for your presentation tonight. We all look forward to seeing this next tranche of research that you've been telling us about that's coming down the pike. I saw in the past week or two things that to me kind of intersected. One was a peer-reviewed study that I believe was in one of the Nature publications, which found that as much as a third of the heat mortality around the world may be attributable already to climate effects. And the other was the World Meteorological Organization saying that it's becoming increasingly evident or likely that we will cross the aspirational Paris target of 1.5 degrees in the next 4 or 5 years. And when you put those two thoughts together, it strikes me that that means we're going to have a serious problem of heat mortality on our hands around the world and right around the corner. Is this getting the kind of emergency attention that it deserves?
Two very important studies, Jack. Thank you for bringing up both of them. I am not sure if the answer to your question is a simple yes or no. It's one of those that if you weren't looking, if you didn't have that feed coming in, you may have missed the stories. And so it's one of those pieces where knowledge is power. And so getting those studies out in front of the folks who need to see it or see them so that they can realize that how critically important time is in all of this, and how critically important this particular impact is, because it's going to intersect with all of the vulnerability pieces that I was talking about before. And how do you start working now with the populations who are probably going to be most affected, right? Because that's the piece that you're working on cutting down the emissions, you're working on mitigating temperatures, but at the end of the day, folks are still going to be suffering, right? And how do you work with the folks who probably are going to be most affected to at least try and alleviate some of that suffering? And for me, people always have to come first. And so that for me is the biggest piece in all of this. How do I, like personally, how do I as a scientist help to mitigate against another human being's personal suffering or community suffering, right? And so thank you for bringing that up. And the second study, the non-WMO one, if you wouldn't mind firing me an email with either a copy of it or the link to it, that would be super awesome.
Sure,
Thank
it
you.
was within the past few days. I think it was reported in the New York Times, but it was, I'll send you the press release that came out from AAAS about it.
Okay.
Thank you.
Jack,
Well,
I'm
thank you.
impressed that you're more up to speed on the climatology research than either of us. And
You're not
I just-
supposed to admit that out loud.
That is certainly not the case, but I did read my aggregations day before yesterday.
Yeah, that's why I said you have to be up on your feed, because there's no way you're going to be able to be on
That's
top of
right.
everything unless you got all these feeds coming in, right?
Well, thank you both for spending your time with us.
Yes.
Oh, thank you.
Yes. Well, thanks. We are at the end of the hour here, and we didn't get to all the questions, but you had some great ones, everybody. Thanks everyone for joining us, and thanks to Dr. Hanrahan and Dr. Dupigny-Giroux. This has been a great discussion tonight. I just want to, I'll pass it on to Rob Kidd with the Sierra Club, but I do want to invite everybody who's here, if you'd like to be more involved in these issues and communicate about what's happening with the Vermont Climate Council and the Comprehensive Energy Plan. Sierra Club is actively working on that and is working with other groups and people around the state who are also doing that. So we would welcome your engagement. And I think probably the best way to connect on that is to send an email to Rob Kidd, who's about to put a slide up on the screen. Rob.
Yes, everyone. So thank you once again for the great conversation. Just for those who just joined us for the first time, we've been doing these for over a year now, and we're going to continue them through the summer. Our next conversation is about biochar and agricultural environment. Then we have a special one on ocean health, something we don't normally talk about that much unless we categorize Lake Champlain as an ocean. I guess it was at one time. But these conversations are going to continue virtually for the time being. But we're also going to be planning on possibly trying to do a hybrid once we can figure out how safe it is to do these events. But we definitely want to continue doing it virtually. And any of those meetings anybody have missed, if you go to our website, you can find on the sierraclub.org/Vermont. I post the recordings within 24 hours of after. So if you ever miss one, just go to our website and under the events tab, you can see under community conversations or political and legislative talks, we have all our virtual events. So thank you all for this great conversation with two doctors who I inadvertently did not label doctors in my promotional materials. So thankfully they didn't notice it, but I corrected it here. So have a good night, everyone. And we're going to be ending this meeting.
See you soon, everybody. Thanks for being here.
Thanks so much.
Everyone.